For 2-methyl-butane, the structure would be CH3, CH, CH3, CH2, CH3. Now how do we draw that? First, drawing the main carbon chain, okay, that is of butane means 4. So this will be our carbon chain, and on the second carbon you have to draw a straight line upwards. Now this straight line could either be, in most cases it should be, okay, it is more appropriate to draw the line of the same length of these carbon chains that you have drawn, okay, because logically if you see, these two are carbons that are attached, so they should also have same distance like these two, okay. Similarly, if you want to show the double bond, like for propene, it would be like this. Propene is like this, okay. You would be showing something like this, a line below it to show the carbon double bond, okay. So these are some of our compounds. Okay, before studying the naming or how to name the organic compounds, we will be studying one concept of functional groups and homologous series. Functional groups and homologous series. Okay. For functional groups, functional groups are basically an identity of a compound. Okay. I recently told you that we have how many? Around 99% of organic compounds, that are around millions of organic compounds. So how do we categorize them? How do I know that what do I call this? Okay, so what we usually do, we categorize something that is in too many numbers, right? So we distributed with categorized organic compounds into different families. Okay, that families we call homologous series. And how do we identify that this compound belongs to this homologous series? By their functional groups. Clear? I would write here functional group is a group of atoms that determines the chemistry, means the reactions, the chemical properties, chemistry of that organic compound. Okay, series of compounds. with same functional group. Okay, now I have a table here. I'll just show you that table. These are mostly the whole functional groups that we will be studying in the whole organic section. Okay, first is the homologous series alkene. Okay, alkene has a functional group. It is sort of very shortly written. It is a double bond between it. Okay, and it is a prefix suffix means that how do we identify that every alkene ends with an ene with it. Okay, so you have ethene, then propene, then butene, and so on. Okay, ethine is not included, but you should know that alkyne means triple bond between two carbons. Okay, but it is not included in our organic section. For the halogen, halogen means that you are attaching an X, where X is a halogen compound, group 7, and you make it like chloroethane. Okay, you attached one chlorine here. It would be chloroethane, bromoethane, so on. Alcohols, you attach a OH group. Ether is not included. Okay, but we'll look into it. Sometimes it comes in different chapters. We have aldehyde. Okay, aldehyde is a very important. You have C double bond O and then H. Ketone, C double bond O, and on both sides you have carbon chain. Okay, so there is no H on any side. So these are ketones. Example is written there. Carboxylic acids, C double bond O and OH. So these are like this. Ester, C double bond O and then O. These are the combination of carboxylic acids and alcohols. These two combine to form an ester. As acid chloride, it would be acyl chloride. Acyl chlorides, okay, C double bond O, and then you have placed a Cl here. Amide, you have NH2 group, okay. Amine, in amine you just have NH2, not C double bond O with it. Okay, then for nitrile, CN group. Okay, this is one of the most important groups, so we'll be studying each and every of them in the organic section. Clear? Okay, should we move to the next topic? Is it clear? Okay, now one of the most important topic, that is naming. Okay, which is nomenclature, but it would be like naming of, to make it simpler. So for the naming of organic compounds, you have to remember some rules. Okay. Rule 1, 2, 3, 4. Rule number 1. First, select the longest carbon chain that includes the functional group. Okay, and if there is no functional group, like if it is just a straight chain, simple chain, then you have to select the longest chain. Then start numbering the chain from carbon closest to functional group. Okay, if same functional group present, use die or try. And if different functional group present, write in alphabetical order. These are some 4 rules that you should remember while naming the organic compounds. Okay, so let us see example number 1. CH3 CH CH2 CH3. This will be CH3, this will be CH3. Now rule number 1 said to find out the longest chain. Okay, if your compound has the longest chain in 2 manners, like if we draw it, I can see that we have a 5 carbon chain like this. Okay, and we have 5 carbon chain straight. So I would prefer the one that is straight. Okay, because it will be easier for me to name the compound then. Clear? So we selected this chain. Now number it. It would be 1, 2, 3, 4, 5. Okay, you can start the numbering from here as well. But I can see that on every side the functional group is on the second carbon. The first, that is the closest one, is at the second carbon. So no matter from where you start, the naming would be same. Now you have to name it. For naming, what you're going to do, you will be writing first. You have to write the number at which the functional group, the okay, we usually don't call it functional group, these are just chains, okay, that are attached with it, or you can say branches with it. So this is which group? These are the ethyl branches. Okay, I will write here. We have ethyl, we have propyl, and sorry, we also have methyl. I forgot to write it. Methyl would be written here. Alkene group. Yeah, alkyl group. Yeah, we can call it like that. Okay, so methyl has CH3. This was C2H5, and this is C3H7. So they just have, these are just alkanes, but they have one hydrogen removed with them, so they are belong to, you can say, to the alkyl group. So for the naming, how we're going to name it? 2 comma then at 4, okay, dash. Okay, how many methyls we have? 2. So I would, what I written in rule 3, that is same functional group, use ditrile. So we will write dimethyl, and the our parent chain was of how many carbons? 5, so it would be pentane. Clear? We can write one more. Okay, let me just wait 5 minutes. I'm just plugging my laptop to the charger. Okay. Okay, continuing. Then we have CH3, CH3, CH, then you have CH2, CH, CH, CH2, CH3. Okay, on this carbon I'm drawing a methyl group. On this carbon too, and on this carbon I'm drawing a propyl group. CH2, CH2, CH3. Okay, try to solve it. First, find out the longest carbon chain that you think is the one. And then you just have to number it with the groups that are present, the alkyl groups. On. Okay, is it done? Mm-hmm. 5. Yeah, but first you have to select the longest carbon chain. Okay, how would I do? Yeah, this one. Okay, this one. So then it becomes okay. So then it becomes much simpler to do it. Like now you have carbon 1, 2, 3, 4. This is 5, 6, 7, 8. So on which carbon this group is attached? Okay, now this is your alkyl group. Now this is not the chain. Okay, now if you have to redraw the chain, this will be the alkyl group. Okay, and which alkyl group is that? That is the ethyl. So you guessed it right. Okay, you were right that it would become 5 ethyl, then 2 comma 4 dimethyl, and then the parent chain was of octane. Okay, yes. mm, Sorry, which one? Yeah, so ethyl, yeah, you're right. Now it is not necessary that if the branching is given of the propyl group, uh, what I told you, that you have to anywhere you have to find the carbon chain. Okay, it could be anywhere, the longest carbon chain could take any path. After that you will be determining the alkyl groups that are attached with it. Okay, then only. But first you have to find the alkane, the carbon chain. It is not necessary that it will always be a straight chain. Moving on to the alkenes. These were all alkanes, right? So for alkenes, how you're going to do that? um, if I have 4 butene, butene is like this: CH2 CH, double bond CH, CH3. Okay, this is one form of butene. Okay, one another form is CH2 CH2, I think so. It would be C1 2, no, it would be CH2 CH3. So what I have done, I have now I have shifted the double bond. Now comes the functional groups. Okay, from now on the namings will be that they will include functional groups. Alkyl is not a functional group. Alkyl is just a branched. Okay, so now we're going to see how the functional groups are being numbered and named. Now, if the chain is smaller of the functional group, but you have to include the functional group. Okay, it is not that you ignore the functional group and you select a carbon chain that is the longest without functional group. Okay, that should not be the case. You have to select a chain that is bigger. Okay, that could be bigger, and it must include the functional group. So in this we obviously have a straight chain. Okay, both are straight chain. We'll just number them: 1, 2, 3 and 4. Now on which carbon the functional group is attached? The first carbon on which the functional group is attached, that is carbon number 2. Okay, so the name would be but 2ene, or you can add 2-butene. Okay, the one that is followed in your college, you can use that one. It would be but 2ene. And for the second one, what could be the name? But 1ene. Okay, I'm drawing a pentene here. CH2 CH, CH, then you have okay, I think we missed one. CH3, CH. Oh, it's getting confused. Let me redraw it. Okay, now we have two double bonds. Chain is straight, so we're just going to select the one. Okay, I selected from this side because here the functional group was much closer, starting much closer. Okay, what could be the name of this compound? See the name. On carbon number 1 we have a double bond, and on carbon number 3 we have a one. So what I written in the rules that if same functional group use di, which means 2, tri means 3, okay, if it is occurring 3 times, and tetra means 4 times, and so on. So no, now you will write it like 1 3. The chain is of pentadiene. Okay, pentadiene. Diatribe will occur. Penta means 5. The chain is of 5 carbons, right? Yes, yes. Okay, next, one more case that if I add now a branch, okay, I'll just take this compound, copy it, and I'm just removing the single bond one. Okay, we'll draw it like this, CH2. I'll draw a branch here, and I'm moving the double bond here. Okay, now we have one alkyl group and one functional group. So always remember, functional group will take the precedence, will be the your priority first. Okay, not the alkyl group. So we'll take the straight chain, number it, and what I told you, alkyl group is not your priority, functional group is your priority. So from which carbon you should start numbering? From this carbon. Okay, and what could be the name? Okay, good. So this is our basic naming nomenclatures of organic compounds. I hope it's clear now. Um, where do we put the dash? When you are connecting the suffix and prefixes. Okay, you can see when I'm numbering, when they are multiple, then you are, for the numbering you just have to use a comma. After that you just have to connect every suffix and prefix with a dash. Okay. For okay, now what we're going to do, we have understood the basic naming. Now we're not going to move forward with every functional group naming. We will be studying them along when we're studying their reactions as well. Okay, then we will be studying their naming in that chapter. Okay, it is quite easy, it is not, but if you get this idea, this concept of naming, the first basic concept, then the further concepts are basically very easy. There's nothing new in that. Okay, you just need to remember the namings of, like, in halogens we use bromo ethane, chloroethane, like that. And you'll get used to them when once you start practicing, okay, the past papers. This concept is also clear. Now what we need to do, naming is done. Okay, we can do now isomerism. Okay, yesterday I gave the lecture of isomerism. Let me show you the notes. We can study with from those notes as well. Okay, I made those notes yesterday. Let me show you. Yeah. Okay, the reason is that it would save us a lot of time if we study from the notes that are already written, but some things we will be writing that are very required, okay, here. So what is isomerism? Do you remember we have studied that in our previous classes in O levels as well, a little bit concept of weight? Yes, yes, different structural formula. That was the definition of O levels, okay, because in that there was not much detail about isomerism. Isomerism is compound is same molecular formula, it is correct, but different arrangement of atoms in space. Okay, isomers must have different names. Isomers, how do we know that one is an isomer of another? They will always have different names. Okay, which means two same compounds but with different faces, different names. That is basically isomers. So whenever you're trying to make an isomer, and if you get a different name, then you can say that it is an isomer. Clear? Isomers are of two type, general broad type. First is a structural isomerism, and the other is stereoisomerism. Structural isomerism has further three types: chain isomerism, positional isomerism, and functional group isomerism. Number three, these are the subtypes that we will be studying. So what is the definition of it? Isomers with same molecular but different structural formula. This was the definition that you studied of isomerism in O levels. This was basically a type of isomerism, that was structural isomerism. Stereoisomerism has also two types: geometrical, that is cis trans we call it, and optical isomerism. Isomers with same molecular formula and structural formula. Okay, what is the difference? They also have the same structural formula, but different arrangement of atoms in space. Shh. Clear? So the isomers will, in stereoisomerism, isomers also have same name, but how we're going to differentiate them, we will study that. First, coming on to the structural isomers, okay, that is first type of chain isomerism. Chain isomerism, from the name you can guess it that chain isomerism arise when there is different arrangement of carbon atoms in the chain. It is written. Okay, when the chain is different, then isomers will be formed. So you can have straight chains, you can have branched chains. Okay, if I have, see, I'll draw these. You have a simple molecule of pentane, CH3, CH2, 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 CH3. This is pentane and it is a straight chain. If I want to make an isomer, I will make a branch. Okay, I will remove one carbon and add it in the branch here, and the rest of the chain will be same. What will be the name of this compound? New compound. Butane. Okay, in here you don't have to write dash. Okay, you can just combine them. Okay, now further, can you make more isomer of it? How? We can add CH3 here and add one more CH3 on the top. Now what will be the name of this compound? Two. Okay, you can write 2 2. Okay, because 2 times methyl is occurring here. Dimethyl propane. Now further, can we make more isomer of it? No. So that is how we form isomers. Okay, and these isomers are occurring because we are changing the chain of carbons. Second is a positional isomers. Okay, positional from the name, which means you are changing someone's position in the compound, and that someone is your functional group. Okay, in the carbon chain you are changing the position of the functional group. So like, see the first example, CH3 CH2 CH2 Br. This is an halogen alkane, and it would be, how do we Br is a functional group, so start the numbering 1 2 3 and it will be 1 bromo propane. Clear? Now you have just what, for positional isomerism you have to shift the Br, so you shifted it to the, placed it to the second carbon. Now it is 2 bromopropane. These two are isomers of each other. And which type of isomers? Positional isomers of each other. See the example 2. First was a straight alcohol, butane 1-ol. Then you place the OH on the second carbon. It became butane 2-ol. Then you placed, what you did, you kept the OH at its place. Now you are doing what? You are Also, doing here is chain isomerism. Okay, you are now mixing chain isomerism and positional. You made a branched. Okay, the name changed. And then again you mix chain isomerism with positional. You place the OH on the downward side. It became 2-methyl propan 2-ol. Clear? Okay, try this. For pentanol, I'll just draw the structure. How many isomers can you form? Try to solve it. Okay, are you able to make them? Is there any confusion? Okay, okay. Shh. Sorry. Hmm. How many you have made? 7. So first one is CH3C. We'll add one branch here. Okay, this will be our first isomer. Then from removing here we can add one branch here. This will be our second. Okay, after that what we can do is we can make another chain. It would be like this: CH, yeah, we can do that also. Yeah, usually it has 7. Okay, it would be 7. Yeah, I'll send you the picture of it, okay, of all the isomers. I remember it had 7 isomers. Okay, moving on to a third isomerism, that is functional group isomerism. Now you are not shifting the place of functional group, you are actually changing the functional group. Okay, the shape, the face of the functional group, you are changing it. For example, you have aldehyde and you have ketone. Both are functional groups, sorry, functional group isomers of each other. How? Because they have same molecular formula. Okay, but their functional group are different. One has aldehyde as functional group, one has ketone as functional group. That is the basic difference. Similarly, carboxylic acid and ester are functional group isomers of each other. You can see from this two compounds, they have same molecular formula but different functional groups. Okay, so in functional group isomerism, positional chain, we are basically doing what? We are changing the structure generally. Coming on to the stereoisomerism, which said that both molecular formula and both structure, the name would be same, but arrangement of atoms in 3D space would be different. So first type is geometrical isomerism, that is cis trans. What is written? It arises due to the restricted rotation about a carbon double bond. Okay, so carbon to carbon double bond is restricted. Why? Because if you remember in chemical bonding, it was a lobe type structure. So this does not allow the rotation. Okay, which type of rotation? Like here it is a different concept. Like I want to move this CH3 to this carbon. Okay, so to move the CH3 to this carbon is not possible here. Okay, in the due to the restricted rotation about the pi bond. So the presence of pi bond makes the rotation not possible. However, in single bond you can do the rotation. So only the rotation that will be possible here would be the sideways. Okay, only the carbon can change its own. Okay, these can be rotated up and down, only one carbon. Okay, not two carbons. That is called a restricted rotation. Clear? So geometrical isomerism is arising due to restricted rotation of carbon double bond due to the presence of pi bond. Now, what is geometrical isomerism? Geometrical isomers, what is written, occur in pairs. Okay, there are, which means you have two isomers of one compound. You have a cis isomer, you have a trans isomer. What is cis? Cis isomer has two groups on same side of the double bond. Okay, you can see the first example, this one. Chlorine, if this has chlorine on downward side, this also has a chlorine on the downward side. Okay. Trans isomer has on opposite side. If it has down, then this carbon has on upward side. They are opposite sides. So this is would be the cis and the trans. Okay. See the naming. 1, comma 2, 1 carbon number 2, carbon number 2, dichloroethene. Oh, sorry, it would be ethene. I have written ethane. Ethene. Okay. 1, 2, dichloroethene. So both have name same. How we are going to differentiate? We will be writing here cis 1,2 dichloroethene and this will be trans 1,2 dichloroethene. Clear? Position of the hydrogen, or yeah, you can say the position of hydrogen or the position of the group. Like if the hydrogen is on the same side, you can say that it is cis. Okay, and the hydrogens are on the opposite side, you can say it, because we are considering hydrogen and this chlorine as a group. Okay, not the functional, we're not talking about functional group, it's just a group of elements. Okay, so it will be chlorine, it could be CH3, it could be any group. Clear? But you have to remember, on each carbon two different groups must be present. It is not the case that hydrogen and hydrogen will be present here. Okay, each carbon will have two different groups on each. Okay, on each carbon there will be two different groups. That is a must condition for the cis trans isomerism. Clear? One more example I did here, like this one. I draw its, okay, cis trans isomers. So now you can see that in cis isomer, always you have to place, now these are different groups. Okay, these are Cl, Br, CH, they are not the same group. But how you're going to now draw in cis, you have to keep the larger MRs on same side. Okay, like for in this carbon, which one has higher MR? CH3. In this carbon, which has higher MR? Br. So we kept them on the same side. And then for the trans, you just have to flip one side, the forward one. Clear? Cis trans has similar chemical properties but different physical properties. The chemical properties means reactivity and sort of solubility, but different physical properties mean melting point, boiling point, density, that would be different. What is written? Cis trans has generally higher boiling point than trans isomer. Now why is that so? Because in chemical bonding, I think I have, let me see. Okay, we have not studied chemical bonding. हाँ,
वो 5 मिनट का ब्रेक लो, मम्मी के अकाउंट में 1000 तो भेजो।
जा रहा हूँ मैं।
जल्दी से भेज दो, मैं सोनू स्ट्रीट जा रहा हूँ डायरेक्ट अभी। स्कूल का 5 मिनट का। नया पेपर।
मोबाइल पे डाल। Oh, okay. So cis isomer has generally higher boiling point than trans isomer. What is the reason? The reason lies in the forces. Okay. We have not studied chemical bonding, but in I think you have studied it by yourself that there's one force that we call it permanent dipole force. Remember? Permanent dipole forces. Those forces occur when there is a net dipole moment, okay, in the compound. So what is the net dipole moment? Net dipole moment occurs when these groups, CH3 type groups, induce their electron charges, because they are like electron, donating groups. So they induce their charges to the carbon. So these are inducing, there is a net dipole moment on the downward side. What does that do? This makes the compound, the cis isomer, polar. From that, it has permanent dipole forces exist, so higher boiling point. Okay, always remember, whenever we talk about boiling melting point, forces are the reason behind it. Okay, the which force is present there, that will determine who will be having the higher boiling point or lower boiling point. So cis isomers have a permanent dipole force as an extra force, due to which they have higher boiling point. Trans isomers, what is written, dipoles cancel out. Okay, one dipole is coming in this way, one is coming in this way. There will be no net dipole. So there will be no dipoles, making it non-polar. So it only has IDID, which means weak van der Waals forces. Only that forces. That is why it has lower boiling point. Is it clear? So we will be studying optical isomerism tomorrow, and we'll do some past papers of isomerism. Okay, so make sure to do revise the concepts. Okay. Okay, bye. You're welcome.